This is going to be a kind of like two-part presentation. So we called it simple access and fast performance. And I guess my part is talking about the simple access, and Ben is really going to be talking about some of the exciting work that they've been doing, kind of really improving the kind of computational efficiency of how we can get at some thermodynamic parameters and yeah, thermodynamic models in certain ways. So this work has kind of been going on for the last couple of years, and I encourage people to like check out our GitHub, read the docs pages, and also for PetThermoTools, the Python package I'm going to be introducing now. We have a YouTube page. There's a whole bunch of examples where we walk through calculations on there, and also recordings from a workshop we did in January. I think we had something around 100 participants in that. But yeah, if you want to walk through the examples we did in that workshop, the questions people asked and stuff, all of that is online on our page. So please do go and check it out. And so most of what I'm going to be talking about today is kind of the work I've been doing, kind of trying to make thermodynamic modeling through the MELTS thermodynamic models more accessible to any user, regardless of their prior coding experience, right? And if we kind of, this is kind of how my mind works for the various different options for running MELTS models. So MELTS in itself can refer to like four different thermodynamic models and a whole range of different kind of software options for actually running those calculations. And the way I kind of visualize it is on one end, you have things like the original MELTS GUI down here, or easy melts for easy melts or melts for Excel. We have these nice GUI or spreadsheet options where anyone can type in a composition, put in pressure, temperature, constraints, and run simple calculations. Okay, you can run some crystallization or some basic melting calculations, but potentially it's a bit limited on kind of other things that you could model. And it's hard to run large numbers of calculations. If you wanted to automate very large numbers of runs, it can be a bit tricky. Back in 2017, I did lots of MELTS calculations for my master's, and I ran something like 2,000 calculations with the GUI. I can tell you it gets quite tedious. Okay. At the other end of the scale, we have things like Enki and Thermo Engine, which you heard a bit about earlier. And as you saw earlier, the kind of stuff you can do in this is incredibly exciting. There's a huge kind of potential for integrating thermodynamic models with other kind of modeling frameworks and doing really more complex stuff in here. To a certain extent, though, for users new to coding or thermodynamic modeling in general, there's a bit of a steeper learning curve. I know to a certain extent, some of that's been overcome with the development of, I think it's called like Magma Forge or something like this. And yeah, in some ways, these things are very kind of high potential, but hard to kind of get started with if you're new to this kind of stuff. And in the kind of center here, up towards that kind of top end as well, we have things such as alphaMELTS and alphaMELTS for Python. So alphaMELTS is I think it originally started as adiabat 1ph, is this kind of command line text-based interface for thermodynamic modeling with the MELTS thermodynamic models that was developed by Paul and Paula Antoshchina. And this was developed, I believe, Paul can correct me if I'm wrong, initially back in 2005, has been developed in various steps since then. And one of the most exciting steps for me, at least, was the release back in, I think it was 2018 or 2019, of alphaMELTS releases for both MATLAB and for Python. And it's this kind of Python release where I've been working with mostly over the last few years. And what my kind of aim for here is to develop a tool which anybody can use, regardless of how much prior coding experience you have. The idea is you should be able to use the kind of tool I've been developing called PetThermoTools. So the Petrologist Thermodynamic Toolbox is kind of how we came up with the name. And the idea is to have this as a tool that anyone can launch Python and use without having to have any prior coding experience, ideally, but also by basing it within the completely open source alphaMELTS for Python, we're providing some degree of kind of customization and flexibility within the calculations for more advanced users. And also it's set up to very easily facilitate automation of hundreds to thousands of thermodynamic models if you wish to do that. And so to kind of just go through very quickly, I want to make sure I give time for Ben to talk about his work. To go through very quickly what we've been doing, we've kind of been packaging up the alphaMELTS with Python functions and methods into PetThermoTools, and we're trying to make it as easy as possible for people to use. So say you want to go and install the package, we can do this through pip, so it's distributed through PyPy. Once you have PetThermoTools installed, all you need to do is then import it into your Python environment and run one installation line. This will download the latest release of alphaMELTS for Python and correctly identify what operating system you're using as well to make sure you get the correct files. It will then add these files to your Python path for that Python environment. So you never have to worry about this again. It's like a one-time thing. You installed it, you're good to go. Once you've done that, using adiabatic mantle melting as an example in this case, all you'd need to do to run a calculation is import PetThermoTools into your Python environment. Here's our kind of adiabatic decompression melting function, and all of our functions work in similar ways. We ask for what thermodynamic model do you wish to use, so here pMELTS, what bulk composition, we have several saved bulk compositions, the KLB1 prototype as an example, and information on your conditions, so the temperature you want to start at, the pressure, ending pressure, the pressure step of this calculation. And we also, within this package, provide various kind of basic plotting functions. So once you have your results, you can plot and visualize those results in various ways. Here, this phase plot function over here will produce a graph that looks something like this. So an estimate of the modal mineralogy of your mantle as it decompresses and moves upwards towards the Earth's surface. And earlier on, we heard from Nicholas Reel about MAGEMin. And in my mind, one of the kind of really exciting things we were able to do with PetThermoTools through collaboration with Nicholas is we were able to not only get this to work with alphaMELTS, but we were also able to get PetThermoTools as a kind of package to work with MAGEMin. And so if instead you wanted to run this exactly the same calculation, exactly the same decompression calculation with MAGEMin instead of alphaMELTS, all you would need to do is change a couple of lines in the installation code. So now we'll install MAGEMin calc. And what this will do is it will set up a connection between Python and Julia. It will install or set up a new Julia environment on your computer, so it won't overwrite or modify any existing Julia installations you have. And within that Julia environment, it will install MAGEMin. Once you kind of in your Python environment, once you load in PetThermoTools, we then need to activate the PetThermoTools environment. This just kind of sets up and activates that Python Julia connection. And then the only other change you need to make, if you want to switch between doing MAGEMin calculations and MELTS calculations, is just change that model keyword argument. So here we'd specify the Green et al. 2025 thermodynamic model. You can run exactly the same calculation and produce essentially the same plot. Okay. So very easily, just by changing one keyword argument, you can switch from MELTS world into the Green et al. 2025 thermodynamic model, easily comparing these different approaches, which is something that has been kind of quite tricky to do in a kind of nice, simplified or concentrated way in the past. And we're continuing to build and expand this package. We have a whole range of different functions that we currently have available. I say, please check out our Read the Docs page and our YouTube videos where we talk through how to run these various different types of calculations in a lot more detail. And these range from things such as simple crystallization through to phase diagram. We have mineral co-saturation estimates to work out the pressure of mineral co-saturation and saturation pressure from like water CO2 calculations in there. You might notice a couple of these things are only indicated that only available for the alphaMELTS, not MAGEMin. There's not any limitation on what Nicholas has been able to do. That's basically things that require the presence of CO2 in your system. So these are only available for the more recent MELTS models released in 2015, where we have that mixed solubility model included. And we're continuing to expand this, or trying to expand this all the time. So the latest thing I actually added was this recent method developed by Aaron Bell, Laura Waters, and Mark Garosso, where you can use the composition of coexisting olivine and spinel phases along with some estimate for the activity of silica in your melt phase to work out the oxygen fugacity of the system. And their method, which includes a modification for the chemical potential of the magnetite component in spinel, is then using all the information is coming from MELTS to estimate the chemical potential of the phthalate component in olivine, the magnetite component in spinel, and the activity and the chemical potential of silica in the melt phase. You can get that information from MELTS and use it to estimate the oxygen fugacity of your system. So that's like the most recent thing I added in. If you have other methods or approaches that you think would be useful to use in this kind of way, just a simple function that can allow people to run relatively simple calculations, please let me know, reach out, and we can work together to get them included in the next iteration of this project. And the final thing that I wanted to talk about before I hand over to Ben is the fact that we're kind of by default running these calculations in parallel when we're working in PetThermoTools. And really the reason for doing this is because when you usually set up MELTS calculations, if you were to do this in MELTS for Excel or most other MELTS software, and you wanted to run multiple calculations, so you're not just running a single crystallization model, you want to run hundreds of crystallization models, let's say. Usually you would set up those calculations in some way. It would go and run the first calculation, wait for that to finish, run the second, run the third, and run these sequentially through time until you finish all your calculations, and it will return the results to you in some way for you to then work on further down your kind of workflow process. The problem is, and this was kind of mentioned a little bit earlier as well, MELTS models aren't always 100% successful. Sometimes they fail. They hit failure points where the model can't find an equilibrium solution. And when that happens, say that happens for run number 2 in here, this would actually then terminate your process in most MELT software options. So in alphaMELTS for Python, as an example, if you tried to continue running MELTS models after this failure point, you'd be met with this message and this secondary message. And basically, if you hit a failure point in this case, you would not be able to run calculation number 3 or number 4 and get the results from those. You would have to completely restart the kernel, reset up your calculations, and then start it from number 3 and continue on from that point. Okay, which is quite tedious, quite frustrating. If you're trying to set up hundreds of calculations, if you're trying to explore parameter space or explore the influence of uncertainties in some of your parameters, it can be quite frustrating if things keep crashing and terminating before you get to your answer. So what we do as default in PetThermoTools is we run these in parallel. We set up our calculations, we then initialize a bunch of child processes, and the calculations are then sent to those separate processes where the calculations are performed. This means each calculation is happening in its own isolated process. So if an error occurs in calculation number 2, calculation number 3 and 4 can continue to run uninterrupted, and the results are returned back to that main process where you then continue to do more work or more investigation with that stuff. We also, if this does happen, will return the results of run 2 up to the point of failure in most cases as well. So we're usually able to catch the results as they come in. And so even if a failure point occurs, we'll still get partial results from those calculations back. And I set up this kind of parallel processing routine purely as a way to get around the issue of MELTS calculations failing and kind of terminating larger runs. But in doing so, it had the secondary effect of having significant benefits for the efficiency of calculations, especially when you're running very large numbers of calculations. We basically set it up automatically to try and optimize your available CPU and RAM available on your machine. And that means for most kind of typical laptops that people have, we can run between 4 to maybe 12 processes concurrently on your machine, depending on the exact specifications of that machine. So for most laptops, if you run approximately 8 calculations at a time or 8 processes in parallel, in most cases, most tests that I've done, you get somewhere between a 2 to 4 times speed improvement, depending on the exact specifications of your laptop. So some tests I ran just earlier, just on my MacBook. This is quite an old M2 chip from 2022. If we were going to run 1,000 fractional crystallization models, this is going from 1200 Celsius down to 700 Celsius with a 2-degree temperature step. So we're talking about something in total of like 250,000 thermodynamic calculations in this case. Previously, with just running these sequentially on my laptop, that takes somewhere between 30 to 60 minutes, depending on which of the 2 laptops I use. When doing these in parallel, you're reducing that somewhere into the range of 10 to 20 minutes. So we're getting a quite significant kind of reduction in the time, in the actual time required to do these calculations. But ultimately, I guess if you're kind of thinking about integrating this with dynamic or geodynamical models, there's still some limitation. Nicholas spoke about this a little bit earlier on as well, and the hash table is a very interesting way to try and kind of maybe provide some further optimization. But ultimately, yeah, we have some speed improvements here. I believe it's quite exciting, quite useful. But if you wanted to really integrate thermodynamic models with kind of dynamical models of magnetic systems, potentially there's still limitations. That thermodynamic modeling is still going to be the bottleneck in this case. So I'm going to finish there. Before we have questions, I'm going to hand over to Ben, and Ben will talk about some of the work he's been doing on this topic.
Thanks, Matt. Can y'all hear me? Hmm. You hear me?
Yeah.
You're quite
Great.
quiet, but
Okay, thanks. I'm quiet. Okay. Maybe I can change my mic to the computer
that's
microphone.
better now, actually.
Oh,
Yeah.
it's better?
Yeah.
Okay. Maybe I just need to be closer to the mic. All right. So I think you can see my screen here. Yeah, I'm going to be talking about the software that Paul and I have been developing for my PhD thesis. We're still like working out the name, but we're calling it NGIBS for now. Yeah, and what this is it's an emulator of free energy minimizers like MELTS or HeFESTO. So I'm going to be using HeFESTO as a case study because I think it'll have the most relevance for this community at this time. But it's completely generalizable to any free energy minimizer. Yeah, and the advantage of this, like over other surrogate models, is that it's completely compositionally free. It's emulating the free energy minimizers like as they come. And it's also all in Python, so I think it generally will also be more accessible. Hopefully, we can integrate it also into PetThermoTools. Um, yeah, I'd also like to, before continuing, just acknowledge that this is building, of course, upon work that we've already heard a lot about and we'll hear more about from people in this community. Lars and Carolina, Hefesto, and also Bob Myhill and collaborators, colleagues for Burnman. I actually have integrated Burnman into this as well for the calculation of bulk properties. Okay, so to continue, uh, NGIBS can provide like a 20,000x speed up on free energy minimizers, which I think is very very impressive. I'm pretty excited about this. It's finally this software product is reaching maturity, and so I'm excited to share it with y'all. So no longer will thermodynamic equilibrium thermodynamics need to be your bottleneck computationally. So you can more intimately integrate them into geodynamic simulations for things that are more complex than we've been able to do previously. So you can do things like model compositionally heterogeneous compositional heterogeneity in general for things like plumes or seismic discontinuities, or if you want to do simulations of subducting lithosphere that's compositionally heterogeneous, for instance, delaminating crustal roots of complex lithologies, or mantle reservoirs that are also um, compositely heterogeneous. So here's a schematic of how it is working. So it's a neural network emulator. And we had to do a lot of refinement over the years to find something that worked well to our satisfaction. But I guess all you need to know is that what the emulator is doing is it's predicting phase equilibria. So we have this lower model that has a binary prediction of phase equilibria, and then from there, those inputs are fed into the upper model, which produces phase abundances and chemistry for all of these phases. Uh, so after that, we have downstream workflows to make those results more relevant, interpretable. So first, we have a least squares optimization to enforce mass balance so that, like other thermodynamic models, NGIBS has the property where we have the same composition in as out. Which is obviously a great sanity check. And additionally, I have vectorized some of the Burnman equations of state and got a pretty good speed up there, about 15x, so that we're able to get both properties from these outputs of the emulator as well. So we'll see a bit more about that. Here's some graphs of the speed up and the computation time. So in my experience, I was getting about 1 to 1.5 assemblages per second running Hephaestus on my machine. And with Burnman, I was getting about 400 per second using the composite class. So yeah, if I'm using really big batches, I can get a much higher speed up with Burnman, almost 100 times. So here I have dash lines, and the dash lines are my bulk property calculations, which are the limiting factor. But they're still decently fast. And then the emulator itself is these solid lines. So Hephaestus would be roughly the 1 to 1 line here. So the line would start here and just go linearly upward, about 4 log units up. Um, So one interesting thing about this, I was kind of surprised to see this, but the gain in performance that we're getting by putting these calculations on the GPUs is somewhat marginal. Um, at least for the emulator in particular, it's something like a factor of 2 to 5. So it already NGIBS is you're getting most of the benefit you can get out of NGIBS running it on CPUs, which is nice because that'll make it much easier to distribute and use a useful, viable product for y'all. Um, and yeah, the benefits with the GPU is more pronounced when we're looking at really high batches on the bulk property calculations. That's we're getting something more like a factor of 10 between the GPU and the CPU when we're talking about 500,000 batches at a time, which actually is a pretty fast calculation within Gibbs. Um, cool. Okay, so let's continue. This is a thermodynamic emulator. It doesn't actually do the real thermodynamics. And so if it doesn't work well, it's not worth anything. And so I'm going to spend most of this talk just trying to convince you that it's producing pretty reasonable proxy results for the real thing. So what I have here at the top is uh, as a function of pressure along a transect for depleted warm mantle from the Workman and Hart 2005 paper. We have the mineralogies, the phase abundances. And at the bottom, I have the emulated version. And the animation here is going up. It's going up entropy. So we're having, a whole isentrope for each frame. So we can see, as we get to higher entropies, the garnet field's expanding, and the ringwoodite wadsleite fields are shrinking. Um, I was very happy to see this because there's a lot of complex behavior here that you can see in the ground truth HeFESTO results that we're also seeing in the emulated version. Except the emulated version only takes 2 seconds to run, whereas the HeFESTO version takes 90 minutes to run. So I think this is a pretty provocative result. Um, I also wanted to just show how the compositional results look. So here I have two ternaries plotted, and I just stuck to one isentrope here, and we're going up pressures up to 40 GPa. So on the left we have iron, magnesium, calcium, and just various phases and their emulations done in HeFESTO and in Gibbs. So the colored markers are the emulations, and the labeled pluses are the results from HeFESTO. I am also pretty happy with this. You can see, for instance, the movement of garnet into the magurite fields as we increase in pressure. Which I think is pretty cool. Definitely the worst is the ferric content of the magnesiolustite. I don't know what's up with that, but it's probably related to the small abundance of ferric iron in the system overall and difficulties in satisfying mass balance. But in any case, I think we'll see that it doesn't really affect the physical property calculations all that much. Okay, so now I'm going to benchmark the equations of state from my implementation of Burnman against the outputs from HeFESTO. So I ran, or this is 4 isentropes. And just as a benchmark, we're looking at density, velocity of P waves, and velocity of S waves. The dotted lines are the Burnman calculations, and the solid lines are the direct outputs from HeFESTO. So there is perfect parity with the densities, which is nice, but I couldn't get perfect parity with anything else because the formulations are both complex and different. And so to what extent this is a problem, I think is probably a matter of taste and something that I would welcome discussion on. But in any case, I think we're seeing qualitatively that they're pretty good. So for the remainder of the talk, I'm going to be benchmarking the emulated bulk properties against Burnman calculated bulk properties using assemblages calculated from HeFESTO, just for consistency. So this is the emulated results versus results calculated from the assemblages in HeFESTO. So this is also dotted lines against solid lines. It's really hard to see the dotted lines because they nearly perfectly agree. This is, by the way, for Workerman and Harzbergite. So we can kind of just see some dotted lines here in the S waves, maybe a little bit here in the densities. but we're getting all the complex um, behavior that we would expect from HeFESTO also out of the emulator. It's doing a pretty good job here. So the calculations for these four isotropes would take 9 minutes on HeFESTO and 2 seconds on nGibbs. Now I'm just going to show off with some things that you can do that I was getting creative with a very fast emulator. So this is a similar animation of modal abundances for a pressure transect for four isotropes. And I used a higher pressure resolution than the previous diagram. And so to generate these calculations, it would take 2.7 days in HeFESTO and 20 seconds with nGibbs, which I was calling it something else earlier, but we're calling it nGibbs now. So yeah, you really get the best benefit out of this tool when you're using it for massive parallelization. So this is just trying to illustrate that. The bigger your calculations, the bigger your win, which I think is something that geodynamicists definitely will appreciate. By the way, I'm varying sodium contents here. I just kind of picked something arbitrarily to vary. So I'm throwing in sodium into Pyrolite from Caracas et al. 2017 and seeing how that changes phase stability, modal abundance. Here's another similar animation where we're, well, yeah, with great power comes great responsibility. And I was doing something that probably doesn't make any sense, but I thought was fun. I'm mixing bulk silicate Earth and bulk silicate Mars and just seeing how the properties change. So what we're seeing here is a gradual transition from bulk silicate Earth to bulk silicate Mars. I have a 300 or a resolution of 100 different mixtures for the two. And you can see things like, you know, in the P waves, these little kinks due to phase changes or propagating up and down as you change your portion of Mars that you're throwing into the blender. You can see your density going up, et cetera, et cetera. The temperature looks a little weird because that's actually also predicted with the neural network. So I think that there's some room for improvement there. Yeah, TBD. These calculations would have taken a day with HeFESTO, 10 seconds on nGibbs. Here's some code of what it would look like. I think I'm going to move past this right quick because I'm running out of time. I have a bit of a training workflow here that we can also talk about. I'd welcome any questions. In fact, maybe I should just stop now while I'm ahead and see if there are any questions. Are there any questions?
I think it would be okay to continue, Ben. Please go ahead.
Okay. Cool. Yeah, I will just talk a little bit more then about like how I made this model. So what I did is I took bulk compositions, bulk rock compositions from the GeoRock database and ultramafic and mafic compositions from the PET database, PetDB. And I added Gaussian noise to all of the compositions, and I took 20% of them and I reserved them for validation so that they were not used in training and I could use them to see how the model would generalize outside of the training data set. And so that's how I benchmarked its performance. So then I basically made these loose isotropes. I was just trying to sample like plausible isotrope PT paths from in Earth from crust to core. So if I did 50% of these training data were produced by these isotropes, and then the remaining 50% was PT grid fine resampling of the phase transitions, because that's the interesting stuff that we really want to know more about. And here are just some statistics about what the data set looks like. This is definitely a simplified version from what HeFESTO handles. HeFESTO handles far more minerals. The reason is because I threw away all simulations that generated phases that were present in less than 1% of the data set because it'd be hard to train on. And so if we wanted to look in composition spaces that would have different mineralogies, we would need to have different trained models. And that's okay and not really too difficult to do. So we'll do that. And yeah, I'm interested in basically what parameter spaces people are interested in exploring, and we can build those models as there arises demand for them. Yeah, here's some more validation exercises that I was doing for the binary model for the predicting phase saturation. We had like classic measures, precision and recall, and then they're compared again against the ground truth abundance and the abundance of the predictions that NGIBS produces. And how the binary the binary model works is for every phase, it actually produces a probability. So it's on a continuum. And we just arbitrarily assign a cutoff at 0.5. And then I enforce that we need to have some assemblage that can handle the bulk composition so that we can do the least squares residual fitting, or it breaks, it won't converge. Yeah, and here's some one-to-one plots. This is what I was using early on in the development of this tool to be able to benchmark how effectively we were emulating HeFESTO. We were doing MELTS at first too, and are doing MELTS, and I have several MELTS models already, but we're talking about HeFESTO here. Yeah, and so I'm definitely pretty happy with these results too in general. I don't know, you're seeing good matches with masses of phases, and then their composition and component space, as well as oxide space. Yeah, and that's all I have. Thank you.